Howdy, in this video I'll be talking about the relationship between EELS and dielectric function of materials. This talk actually started from a discussion I had with Dr. Demkovich, Dr. Schemberger, and Dr. Chen in our department. So the question was, how can we measure the dielectric function in TEM? The answer is we can always use EELS to probe the dielectric function of a material. Then a follow-up question came up. The question was, does it measure the low frequency or high frequency dielectric response? Back then, I didn't know the answer. Then Dr. Chen told us EELS probes the high frequency response. So I went back and read more on this topic, and I'll share what I've learned with you in this video. Here, I'll cover three things. The first is what the dielectric function actually means and what it tells us about a material. Second, does EELS measure the low frequency or high frequency dielectric response of a material? Third, how to get the high frequency dielectric information from EELS. Let's start from the basics. We often hear about dielectric constant, usually denoted as epsilon. In static situations, say for a capacitor, we treat epsilon as a single number that tells us how much charge the material is able to store compared to vacuum. But in general, this constant is actually frequency dependent. So instead of a single number, we have a complex dielectric function written as epsilon omega equals to epsilon 1 omega plus I epsilon 2 omega. The real part, epsilon 1, describes how much the material can store energy, how the electric field is screened or slowed down. The imaginary part, epsilon 2, describes how much energy is lost through absorption, excitation, or other dissipation processes. So together, epsilon omega tells us how electrons collectively respond to an oscillation of the electromagnetic field over a wide range of frequencies. Let's look at the figure from Wikipedia. At low frequencies, the response is dominated by things like ionic polarization, atoms physically moving under the field. As frequency increases, this slower mechanism cannot keep up, and only the electrons can respond. So the dielectric constant decreases with frequency and eventually approach the optical or high frequency dielectric constant, often called epsilon infinity. This is the regime that EELS is sensitive to. Before venturing further, let's have a closer look at the dielectric function and the dielectric constant. Dielectric constant is a measure of polarizability. The dielectric constant is a measure of a material's ability to polarize in response to an applied electric field. This polarization reduces the effective field inside the material. So a higher electric constant indicates a greater polarizability, meaning the material can store more electric energy. The dielectric constant tabulated in undergrad textbooks is typically the static dielectric constant epsilon s, which is the real part of the dielectric function at zero frequency. That's when omega is approaching to zero. This slide contains more information on the real part and the imaginary part of the dielectric function. One thing I'd like to draw attention to is the imaginary part of the dielectric function, because this is what EELS measures. In fact, in EELS, what we actually measure is not epsilon omega directly, but something we call the loss function. This describes how much energy a fast electron loses as it passes through the material, essentially how much the material's electron gas could be excited at a given frequency or energy. The peak in this loss function corresponds to the collective oscillation of the electrons known as the plasmons. So does EELS probe low or high frequencies? Think about what's happening physically. The electron beam interacts with the material at energy losses of tens of electron volts. That's equivalent to frequency on the order of 10 to the 15 Hertz. much higher than the phonon or ionic vibration range. Therefore, EELS effectively measures the high-frequency dielectric response dominated by the electronic polarization. Now, let's look at how we can use EELS data to get epsilon omega, that's the dielectric function. We start with an EELS spectrum that includes a low loss region, typically below 50 eV, where features like plasmons appear. For a metal like aluminum, the bulk plasmon peak usually occurs around 15 eV. This peak contains key information about the collective electron behavior and therefore about epsilon omega. Next, we can extract the dielectric function. First, we remove the plural scattering, that is, electrons that have lost energy multiple times, by deconvolution. Then we isolate the bulk plasmon peak and model it to obtain the single scattering distribution. From the measured loss function, we can calculate the imaginary part of the dielectric function. Finally, use the Kramer's chronic analysis, or KKA. We can reconstruct the real and imaginary parts of epsilon omega. When applying this procedure to aluminum, we should find that the extracted high-frequency dielectric constant is around 1.5 to 2. Here are some takeaway messages. First, the dielectric function describes how a material stores and dissipates electromagnetic energy. It connects directly to the material's electronic and optical properties. Second, EELS primarily probes the high-frequency dielectric response because the energy losses correspond to the fast electronic excitations. Third, by analyzing the plasmon peak in EELS spectrum and applying the KKA or the Kramer's chronic analysis, we can reconstruct the complex dielectric function and estimate the high-frequency dielectric constant of a material. Finally, I would like to acknowledge NSF DMR for supporting this work.